But before I start, let's start with some basic definitions. So I'm talking about feature encoding of categorical data. But what is categorical data? That's any data that you can think of putting into some groups. So think of cities, names, professions, anything like that. Now, this data usually holds a lot of information, and it is very useful to put into models. But there is one challenge, and that is that, with some exceptions, most of the models need numerical data to work well, to be able to read and understand the data. So what do we have to do? We want to transform this categorical data into numerical, as simple as that. And this is actually the part which we call feature encoding, and that's what I'm going to give a talk on today. So, like I said, I work in payments. Payments sounds like a lot of numerical data, sure, because we have a lot of information on payment volumes, right? But it also has a lot of categorical data. Think of payment methods, payment status, IP address, country. These are all categorical data points that we work with. So just a heads up, some of my examples later will have information from the industry, something about payments, but I try to keep it very simple. So how I got motivated for this talk is actually from a challenge that I faced on my own while working on one of the projects with the classification model. I was working with a lot of with data points that had all of the countries in the world, and that required encoding the countries in a proper way. Now, because of the cardinality of this data point, which is around 200 countries, it was a challenge. And that motivated me to look into all the different possibilities of feature encoding and then choose the best one. And that's also the goal for today. But before we start, I want to see by a show of hands. So how many of you here ever used categorical data during model development? Okay, that's great. And how many had any challenge while encoding it in some way to help the model? Yeah, great. So, well, I'm happy to hear that, and I hope that today's session will help with taking some future steps. So before we start, I want to ask all of you to think about this challenge that you had with categorical data and keep it in your mind while I'm presenting. Then hopefully one of the approaches that I present is something that you can try in your work and hopefully make your models work even better. So the plan for today is the goal is we want to learn about different encoding methods and how to choose the right one that you need. I'm going to start with a couple of stages of starting from simple ones to advanced. For each of them, I will say when to use it, when not to use it, and things that are important to pay attention to. So you will also see this little icons to notify what I'm talking about. And in the end, heads up, there will be a QR code with a summary of everything I'm going to say. So that's something you can take home with you and hopefully use in your work. I'm also going to say all the Python libraries that you can use to use this encoder. So everything I'm going to show today can be found at least in one of these Python libraries. So then let's start. The first one. Basic encoders, what I call basic encoders. Let's quickly go through them. They're more well-known. The first one, the ordinal encoder. So this is as simple as mapping each value to a distinct numerical value. We use it with ordinal data. For example, when we talk about educational levels, we have different levels of education. We can map it to a single numerical value, and then our data looks like this. Right? So it kind of makes sense that when we order it, we see that master's comes after bachelor's and then comes PhD. But don't use it when the data is not ordinal, because then you introduce ordinality which is not present. So for example, with eye colors, we can do it, sure, but then it sounds like blue is twice as brown, which doesn't really make sense contextually. So not a good idea to use it. Later we'll see what is good to use for this one. The second encoder is the frequency encoder. Here is also a simple one. We map each value to the count that we see in the training set. It's nice to use with high cardinality because it decreases the cardinality. And it's, of course, you have to think of the use case as well. Does it make sense? So for example, here, if we're talking about selling products, how much a product is sold, it's how much we see it on our data, could give us context. So for example, here we see 3 chairs, we did 2 tables, 1 plate, we encode our data, it looks like this, and our model knows how much the products were popular in the past. So we teach our model something. But it's not really nice to use it when all of our categories have equal number of observations. For example, here, when we encode, we see only trees. So it doesn't really teach the model anything, and chances are, if you do use this one, the feature will be dropped at some point during feature selection, so you might as well save yourself a step and go for another encoder. And the last one from this group, well-known One Hot Encoder. We create a binary feature for each category. It's nice to use with lower cardinality because then we don't introduce too much sparsity in the data. So for example, eye color example comes again, but this is when we should use it. So here we have 4 different eye colors, and we make a binary feature for all of them. One tip, you can skip the last one to avoid multicollinearity, then that value is encoded with just zeros. But be careful, because if you have a lot of new values that come in production, they will all be encoded the same way. So something to keep in mind, and of course, decide based on your use case. When not to use it, like I mentioned, high cardinality data. For example, days of year, we have 365 days, and if we encode with One Hot Encoder, it looks like this. Not really nice for any model. So here we avoid it. And with that, we conclude the simple encoders. And we go to part 2. This encoder, simple but powerful. I also like to think of them as a bit of helper encoders. There are 2 of them. The first one is the rare label encoder. What we do here is we group infrequent categories into one rare category. Let's see how that looks. So here we have an example of data that shows payment methods. So all of this that you see here are different payment methods. Some of them are international, some of them are specific to different countries. So we see some repetition, like Ideal, credit cards, Klarna. They repeat itself during within the data. But there are a couple of examples, like this tree, that we only see once. And this is not very sufficient to teach a model anything. Probably it will start overfitting. So what can we do instead? We can group all of this together into one rare label category. So basically what we're doing here is we're just grouping everything together in one new category that we will treat everything together. And something to mention here before I go on is that be careful, we are encoding, but we are still dealing with categorical data after this encoding. So after this, you still need to apply one more step to get numerical data. So you can apply one of the other encoders that convert to numerical data. And that's why, like I mentioned, this is like a helper encoder. So you transform your data up until some stage. When it's not so nice to use this is when the rare values are meaningful. There are some circumstances like that. Let's see, okay, the same example with the payment methods. We have the 3 with the 3 rare ones, we encode them. But then in production, we see also a new one. And then we blindly allocate it to the rare class. And that's not really nice, especially in this case, if we think that, okay, Apple Pay was a new product that was introduced after we put the model in production. So now this new product, we treat it the same as everything else that before was underrepresented. And in this case, underrepresentation could mean that the product wasn't doing so well. And now the new product, we treat it the same way. It means that maybe we're not even giving it a chance. So all I'm saying here is not impossible, but check with your business, check with your stakeholders if it's possible and if it makes sense, that we're not putting the conclusions out of the model in danger, that we're not inferring wrong decisions. Hash encoder is the next one I would like to cover. And what happens here is that to each value, we apply a hash function and we create hash buckets. It's nice when you have very high cardinality, as we'll see in the example. Why it's nice is because it's very memory efficient. It calculates everything on the fly, so you don't need to store anything in memory. And it reduces dimensionality of that high cardinality. I like the example of author names because it's an example where we can have millions of names. There are like millions of authors in the world, right? So all of these authors, if we're building a model related to books, and author name is one of the features, then what happens is that we have very high cardinality, right? So what we can do here is we apply some hash function and we bucket them. How do we apply this hash function? We choose a hash function, and then the second thing that we have to define is the mod. So the number of buckets. How many buckets do we want to group the values in? This number of buckets is then inputted in a mod function to create the bucket. So let's just see it with an example. So for example, if we have a hash function applied on this three authors, the mode of the number of buckets that we decided was 0. In this case, it was 1. In this case, it was 3. It was 2. So basically, here we had 3 buckets defined, and the possible remainders of 3 are 0, 1, and 2, and that's why this works. It buckets everything into three groups. So what is nice here is that from having, well, in this case, like five orders, we ended up with only 3, right? So this is like going from 5 to 3. That's a very simple example, but in reality, it would be from thousands or millions to much less. So that's something you could do. Don't use it on ordinal data, because then you introduce a relationship where it doesn't exist. Possibly, for example, here with subscription, if we applied a hash function and by any chance basic and premium were grouped together and standard was separate, then the model won't be able to that easily infer that basic and premium don't make sense to be in the same group because they are far apart on the scale. So that concludes the second part, and we're moving to the last part, the advanced encoders. We have 3 of them, and these are very interesting to see. And the biggest difference between what we saw so far and what we're seeing here is that these encoders don't only use information from the feature itself, they also use information from the target. And let's see how. So the mean or target encoder, we simply calculate the mean of the target for each category, right? It's nice to use when you have high cardinality to decrease it, and use it for when the target is continuous or binary. For multi-label, there is a trick I'll show you in a bit. So let's see, when we have, again, we have a payment method example, and in this case, we just see the payment method of a payment and whether it was fraudulent or not, so 0 and 1, binary target. How would we encode this? Well, we first take ideal, right? And we will see all of the target values that ideal has. That's 0 and 0, and the average of 0 and 0 is just 0. So ideal will be encoded to 0. On the other hand, Klarna has one target of 1 and one target of 0. So it means that the average of that is 0.5. So our encoding will be 0.5. Similarly, for credit card, we have 2 ones, 1 0, average is 0.66. So this is how our data looks like afterwards. You see, from having all these categories, we ended up with continuous values, which can be very informative for the model. That we are kind of inferring how much fraud. Technically, in simple terms, it would be to say we are saying how much fraud was present in each payment method in the past. So this can be very powerful and bring a lot of knowledge to the model. Something to be aware of is data leakage. If you want to be extra careful, what you can do is decide to use the leave one out approach, and that means that you are for every single row from a specific category, you will calculate the average of everything else with the same value without considering that row itself, because in production you don't know the value of that row yet, right? So to avoid this, to avoid calculating something that technically in production wouldn't yet be known, we can use the leave one out approach. And with multi-label, the other trick is here we have, you see the difference is that here the target label, it's not fraud anymore, it's status. So it's not binary, it has 3 different values, paid, canceled, and declined. And the trick here is that the label is categorical too. So we have a categorical feature and we have a categorical label. What do we do? One trick that we can do is we can one-hot the target itself. So here you see how we are actually using a combination of 2 encoders. We are using one-hot encoding for the target, and only then we will use the target encoder on each of the values of the encoded target label. So that's the trick that you can do if you have multi-label. When not to use mean or target encoders, when you have dependencies between your between the features and the feature-target relationship changes over time. There's another one you can use then. But why it's not nice is because, for example, here we have payments of, in this case, credit cards, and also we have the country feature. we can see that the country can be quite indicative of whether it's fraud. Like whenever you have country A, it's fraud. Whenever you have country B, it's not fraud. But as we saw in how we calculated the payment method encoding, everything gets encoded to 0.66 for credit card, right? They all have the same encoding. So actually then we asked the model to figure out this relationship between the country and the payment method. And what could be nicer is actually taking a step back and maybe going to feature engineering again and maybe finding one feature that would represent both payment method and country together, even if that means concatenating or something like that. So that's something to take into account. Weight of evidence encoder. It's similar to target encoder, but here we don't calculate the mean of the target. We actually calculate the ratio between the goods and the bads in a simple way. This is the formula. So we take the logarithm of the probability of the goods and the probability of the bads. This might be also, or you might be familiar with this under the name of log odds. And log odds is something that is present in logistic regression. So therefore, this encoder is quite nice to use with logistic regression. So when you're doubting between target encoder and weight of evidence, but you're working with logistic regression data, this could be a good way to go. An example is, we look at the probabilities of the goods and the bads, and we calculate the logarithm of their after dividing them, and we end up with the value for each of the different categories. How the model understands this is that when we get a positive value, it means that there are more goods than there are bads, and the other way around, when we have a negative value, it will understand that there are more bads than there are goods. And basically, the higher the absolute value of this calculation, it will know that there was that much more difference between the goods and the bads. So that's in this case, this is how the data will look like. And like I said, it's then nice to use in logistic regression. When it's not so nice to use this with ordinal data, why? It's because then we treat meaningful intervals as equal. So in this case, there are better ones to use, like we saw earlier. Like it's possible to do, but it's not advised. The last one I'm covering today is the cat boost encoder. And in simple terms, I would say it's time-aware target encoding. Why is that? It's because this one, it works the same as the target encoder, except that we first order all of the values according to a specific time. So if your data has a time component and there is time-aware, there is dependency between the target and your feature, then this one is a good idea to use. And if you remember, this was the downside of the target encoder. So this is how we fix it. This is an alternative that we can use in that situation. An example I gave again is the payment methods. So here, something important to say is that for every row, we will calculate it separately. It won't be one calculation per class anymore. So for example, for credit card, let's say the last row of credit card, what we will do is we will take all of the credit card rows that we saw before. We will calculate based on these data points, and then we will apply that on the last data point. So basically, we'll find the mean of the previous ones and then apply to the last one. And then we do that for each row, and where we take into account all the preceding rows of that same category. And when not to use it is when you have limited data or we have very large feature sets, because then it becomes very computationally expensive. Because like we saw, there is a lot of, we make a calculation for every row, so it will require a lot of computation. And finally, when you have dependencies between categorical features, similarly as in the target encoder. This example is when we have very little data. So here we're looking at medical symptoms and leg and arm pain. They have too little information to teach a model. Something you could do here is consider using rare label encoder first and then continue with cat boost encoder. So that wraps up everything, all the content that I wanted to show on the feature encoders. And before I finish, I would like to show you how I solved my challenge. So how did I represent countries' data in the model that I used? It was regulatory model. Why I emphasize it is because, well, basically, I worked with countries' data, and regulatory model imposed the restriction of only using logistic regression, right? So it wasn't possible to use fancier models. First try, One Hot Encoding, it would look something like this. It's not really a good idea. So what we do instead, we've went back to the country itself, and first we noticed a lot of countries that don't appear so often on the data set. So first thing to do is the reliable encoder, and that prepares our data in a way that the model will have enough information to learn from. And the next step was decided, as you can probably guess, because of the restriction on logistic regression, use the weight of evidence encoder. So this was the way to fix, to solve the challenge of encoding country names. I will leave you with one last remark. Always fit transform on train set and transform on test and production. That's very important to avoid any data leakage with your future encoding. And now, as promised, here is the summary, the QR code. You can see everything, when to use, when not to use, all the examples that I showed, what to pay attention to, and also you have all the Python libraries with links to the specific methods that you can use to put these encoders easily in scikit-learn pipelines. Thank you very much, and I'm looking forward to your questions.
So thank you very much, Ana. Would you prefer to sit or
Yeah,
we
sure.
stand? Okay, so I was rude. I didn't invite our previous speaker to that. Sorry about that, to Tiago. Okay, so we have several questions. The most popular, actually very popular, is how do you deal with categories that are not found in the training data, only appear at test time?
How do you deal with the categories that are...
So for instance, a new country is
Yeah.
created. You train your data with only the old countries. How do you deal with a new country that is created?
Yeah.
Not very common.
Yeah. No, it is actually, yeah, it's a very good question. And so the thing is, some of these encoders have the ability to handle unknown values as well. So for example, the hash encoder, it calculates everything on the fly because it just applies the hash function to any new value that will come in. So with that one, you don't have the problem. With other ones when you could have this problem is you could decide to bucket everything into one unknown class and then treat everything as unknown. And another thing you could decide is also say, okay, you pause the model, you review what is possible, you do some retraining, and then also continue with the pipeline as it was. But the trick with hash encoder, for example, the hash encoder, it handles everything on the fly. And what the second thing that you could do is it's kind of similar to what the reliable encoder does, that it buckets everything in the reliable class. You could bucket into unknown class. And one last thing is that a lot of these encoders have parameter in them, like when you use the method from Python, they have a parameter inside where you can specify how you want to handle the unknown values. Mm-hmm. So you could decide to throw an error, and then your model stops. It doesn't produce an output. It warns you that, okay, something is wrong. You have to you need to have a look. Or you could decide to do one of the other things that I just said. So that's possible to specify already in your pipeline.
Okay, thank you. So there are actually a couple of clarification questions about the hash, the hash encoder. What's the criteria to group the values? And can you give an example of how this works? Because I think the issue is what you showed. So the semantics of having two values in the same bucket is not really clear. And I think that was the same doubt we had.
I mean, I agree that this is the most controversial one. It feels kind of random, right? You apply a hash function and then things get grouped, but you don't know how. I would say that to use this one, you have to also test that it really doesn't decrease your performance. So if your model benefits from having categories grouped together, then use it. But if it actually leads to information loss and wrong groupings, for example, like with the subscription types that we saw, then it's not a good idea to use it. Yeah. So there is some level of, well, there's a lot of level of randomness there, because you apply a hash function and technically you don't know in which bucket each of them will lead. But like I was saying in the when to use this one, it's because of very high data cardinality. So if this is the biggest issue you're dealing with, the cardinality, and it's not the performance, then it's worth trying it. Yeah. So like with author names or so.
Okay, so the audience is pushing us for the final question, which is, have you tried applying multiple ways of encoding the same variable and then doing feature selection?
Yeah, that could be also possible. Why I like this, why I wanted to give this presentation is because there are a lot of encoders out there, and if you include all of that in your feature selection and you have a big data set, it might become very computationally expensive, very long. So you always have to do some filtering in the start, and that's where this presentation, I hope, will come in handy. But another way that you could do is for sure include multiple encoders, and then compare performance, which one leads to the most. And here I also want to just remind what I was mentioning in the start. If you had any problem that you worked with at work that involved categorical data, hopefully one of these encoders seemed at least a little bit applicable. So when you go back to work this week, hopefully you can try it, and maybe even with the help of the summary, see if it can boost your model performance.
We're out of time, but
yeah.
I'm going to push it. I have one question, because your last answer pointed into the direction of the curse of dimensionality, which in this encoding is, I think, very important. But you haven't discussed it. Didn't you ever find this problem?
Could you clarify that?
The curse of dimensionality, the fact that by encoding a nominal variable into multiple variables, it will increase the dimensionality of the data set.
Yes.
And then the possibility of overfitting increases.
Yeah, but do you mean when you introduce multiple features?
Multiple features by encoding once.
Yeah, so that happens for sure with One Hot Encoding, right? And that's why we are avoiding One Hot Encoding when you have high cardinality. But with all the other methods that I was showing, actually you end up with only one column. So that's only one added feature. Actually, you replace your feature with another feature, and that doesn't add to your dimensionality.